Let's briefly look at the equation that we're using to calculate t for in the t-test. This is the most complete version of the equation for t. This is the one that we use for two independent samples. Um, it's uh, um, it's kind of like the test. What in the numerator we have the difference between the two averages, like the difference between Al's group and Bob's group. And so instead of having a z-score, we've got a difference between two averages. And then we divide it by the square root of the weighted variances. This looks like a nightmare down below here, but what we have are S1 squared and S2 squared. So that's S1 is the standard deviation of the first sample, S2 is the standard deviation of the second sample, and squared is what we call the variance. And so what we want to do is we want to weight this by the sample size, which is what all this N1 and N2 is, and then take into consideration down here in the numerator the degrees of freedom. So it's kind of like giving the average variance, the numerator, and this phrase are the weighted variance, and then we kind of make it into an average variance by dividing by the degrees of freedom. And the degrees of freedom are the size number of samples in the first sample and in the second. They don't have to be equal, they can be very different. That's what makes it so versatile. And then we get that average weighted variance and we take the square root. And so it's basically like dividing by the difference in the values by a variation of the standard deviation. So that seems fairly similar to a z-test. And so that's why scores tend to be similar to z-scores. And a rule of thumb is if they're around 2 or greater, they're going to be significant. But that, of course, depends on the degrees of freedom.